An array is a collection of elements, each identified by an array index. All elements in an array must be the same type. Arrays are used to store multiple values in a single variable, and these values are stored in adjacent memory locations for efficient access. You can declare an array using the square bracket. Integer tests, then inside the bracket we have 5. This declaration tells the compiler to allocate space for 5 integers and to associate that block of memory with the variable name tests. The indices for this array will range from 0 to 4. Integer test, square bracket 5. The first part is int keyword, which specifies the data type of the elements we are going to store in the array. In this case, all elements must be integers. This sets a uniform type of all the elements, making it easier for the compiler to optimize storage and access. Array name test is the identifier or the name of the array. This is how we will refer to the array in the rest of our code. Naming convention matter. Always try to give array names that are indicative of the data they hold, making the code more readable. The square bracket 5 following the name is the size declarator. This indicates the number of elements the array can hold. Here it is 5. It is essential to note that in language like C or C++, the array size is fixed at the time of creation and cannot be changed later. The size of the entire array in memory can be calculated as a product of the number of elements and the size of each element. In this example, if an integer occupies 4 bytes, then the array test would take up 20 bytes, so 5 elements multiply 4 bytes each. The size of an array isn't just about the number of elements it contains. It's crucial to consider the data type of those elements as well. The size is actually the total number of bytes allocated for the array. The formula to calculate the size is straightforward. You simply multiply the number of elements by the number of bytes required for a single element of that data type. This is particularly relevant when you are working with memory-sensitive applications or low-level programming language. For example, if you have an array test with 5 integers and you are using a system where integer takes up 4 bytes, then the total size will be 5 multiplied 4 equal 20 bytes. Similarly, you have an array measures with 10 long double elements, and the long double take up 8 bytes in your system. Then an array will occupy 10 multiplied 8 equal 80 bytes. So knowing the size is important for memory allocation and management. Named constants are constants that are given name for a better code readability and maintainability. You can define a named constant using const keyword followed by the data type and then the constant name. For instance, consider line const integer size equal 5 semicolon. Here, size is a named constant set to 5. We can then use this named constant when declaring the size of the array. Integer test, then in the square bracket, just put size. Every element in an array is assigned a unique subscript starting from 0. Think of this as an address that helps you locate specific data within the array. It's crucial to note that the array subscripts typically start at 0, not 1. This might take some time to get used to it if you're new to programming, but it's a standard convention in many languages. So why start at 0? One reason is that it makes some mathematical operations and calculations easier and more efficient. The index essentially tells us the offset from the start of the array. We have discussed that the array subscript start at 0. Now let's focus on how to identify the last element in an array. A straightforward rule helps us identify the last element subscript. The rule is n-1, where n is the total number of elements in the array. Here, n is the number of elements in the array. For example, if your array has 5 elements, n equals 5. So let's revisit our previous example. Integer tests, then bracket 5. So this array has 5 elements, so n equals 5. Applying the n-1 rule, the last element subscript will be 5 minus 1 equals 4. Therefore, test square bracket 4 is the last element in the array. The elements in an array can be treated just like regular variables. You can assign values to them, perform operations, and use them in output and input statements. For example, you can assign the value 79 to the first element of an array named test using test square bracket 0 equals 79. To output this value, you can simply use cout test bracket 0. This will print the value 79 to the console. If you want to get a value from the user, you can use cin greater than test bracket 1. This will store the user's input in the second element of the array. You can perform operations involving array elements just like any other variable. For example, test bracket 4 equal to test bracket 0 plus test bracket 1. It will sum up the first and the second elements and store the result in the fifth element. One thing to note that you cannot directly use the array name in the certain operation like output. For example, cout tests is not legal and won't output the array elements. To output or manipulate an array, you need to work with its individual elements. This program asks the number of hours worked by 6 employees and stores those values in an array. It then displays the recorded hours. As discussed before, we are using a named constant name num_employees set to 6 to make the code more maintainable and understandable. We declare an integer array called hours with a size determined by num_employees. The program then uses cin to read the number of hours worked for each employee one by one. Notice how we are accessing individual array elements to store these hours. After collecting all the data, the program uses cout to display the number of hours stored in the array. Again, we access individual elements of the array for output. This example is straightforward, so we manually wrote each cin and cout statement for each array element. However, in a more complex program, you would likely to use loops for such operations. Imagine if the number of employees changed in the future, we'd only have to update num_employees constant, making the code easily adaptable. The simplest way to access an array element is to use a constant or literal as the subscript, like test bracket 3. This directly accesses the element at index 3 in the array tests. The method is straightforward and useful when you know exactly which element you need to access. Array also allow for more dynamic access through integer expression. For example, you can use a variable like I as the subscript to access an array element in test square bracket I. So using a variable as a subscript is especially useful in loops or conditional statements where the exact index may not be known in advance. In our sample code, we define an integer I with the value 5 and then use it as a subscript. This is functionality equivalent to using test square bracket 5 directly, but adds the flexibility of changing I during runtime. Note that the expression used for the subscript must evaluate to an integer. Floating point numbers, strings, and the other non-integer types are not valid subscripts. So far, we have seen how to manually assign and access individual elements in an array. Let's look at a more dynamic way to initialize array elements using a loop. As a best practice, we are using a named constant array_size set to 5. This allows for easier future modifications and makes the code self-explanatory. We declare an integer array numbers with the size of array_size. Instead of assigning values to each element one by one, we employ a for loop to handle this task. The loop starts with a counter count at 0 and increments it until it is less than array_size. Inside the loop, we assign the value 99 to the array element corresponding to the current counter value. For example, numbers square bracket count equal 99. This method is especially useful when you are dealing with larger arrays. Imagine having an array of 1,000 elements. Using a loop becomes almost necessity. Note that we use count less than array size as our loop condition. This ensures that we respect the n-1 rule we discussed earlier, as the last index will be array_size -1. The for loop begins with the declaration of an integer variable count, which is initialized to 0. This variable will serve as the array's subscript during each iteration of the loop. The loop continues as long as count is less than array_size, ensuring that we don't access elements outside of the array's boundary. The statement numbers bracket count equal 99 is executed during each iteration. This effectively assigns the value 99 to each element in the numbers array. At the end of each iteration, count is incremented by 1. We start with index of 0, in line with the zero-based index of arrays in C++. The loops end when count is equal to array_size, which means the last executed index is array size minus 1. So this is n minus 1 is the last index rule for arrays. When an array is declared as global, all of its elements are automatically initialized to 0 by default. When an array is declared within a function, making it local to that function, its elements are not automatically initialized. They contain garbage values until they are explicitly set. In this example, we define an array test with a size of size. Immediately after declaring the array, we initialize its elements using a list of integers enclosed in curly braces. The values in the initialization list populate the array in the order they appear. For example, 79 is assigned to test bracket 0, 82 to test bracket 1, and so on. It is important to note that the number of elements in the initialization list cannot exceed the array size. In this case, size is set to 5, and the initialization list also has 5 elements. Using initialization lists can make the code more readable, especially when the array is small and each element has a specific known value at the time of declaration. If the initialization list has fewer elements than the array size, the remaining elements will be automatically initialized to 0 in C++. If you attempt to initialize with more elements than the array size, the compiler will generate an error. The program begins by declaring a constant named month, set to 12, representing the number of months in a year. An integer array days is initialized using a list. Each element in the array represents the number of days in the corresponding month. A for loop is used to iterate through the array. It starts with count set to 0 and runs until count is less than month. Inside the loop, the program displays the month number, count plus 1, and the number of days in that month. So days bracket count. Notice the use of count plus 1 for displaying the months. This is because arrays are 0-based, but months are generally counted starting from 1. In this example, we declare an array numbers of size 7. We only provide initial values for the first 4 elements. In such case, C++ automatically sets the remaining elements to 0. So in this example, the array numbers would look like 124A, then 000. C++ can determine the array size for you. So in this example, we have an array called quizzes. We didn't provide any size, but we did provide an initialization list with 4 integers. In such case, the compiler will automatically determine the size of the array based on the number of elements in the initialization list. Here, the size will be set to 4. It is important to note that you must provide either an explicit size or an initialization list for an array. You cannot leave both unspecified. Using an invalid array subscript, like trying to access number 10 subscript when the array only has 5 elements, results in undefined behavior. Undefined behavior means anything could happen. Your program may crash, you could corrupt memory, or you could inadvertently introduce a security vulnerability. So one might ask, why didn't C++ check the bounds? The primary reason is performance. Adding a check for every array access could slow down the programs, which may be unacceptable in performance-critical applications. You can manually check that an index is within the array bounds before using it. This adds a layer of safety to your code. This example demonstrates a risky practice, attempting to write more elements to an array than its size. So it's a classic case of array index out of bounds. Size is set to 3, defining the array size. A for loop runs from 0 to 4, trying to store the value 100 as these indices in the values array. C++ doesn't perform any bounds checking, so the code will compile and run, but it will produce undefined behavior. Undefined behavior means that the outcome is unpredictable. It might work sometime, or it might lead to program crashes, data corruption, or security vulnerability. This is what happened. The array's values is set up in 3 elements, so value 0, value 1, and value 2. And if you assign the elements out of the bounds, so value 3, value 4 are out of the array bounds, so anything previously stored here is overwritten. The outcome will be unpredictable. Writing to or reading from an invalid array index can corrupt other locations in the memory. It can lead to unpredictable behavior in the same program or even in other running programs. Accessing invalid indices can lead to crashes, which is usually the best case scenario since it makes a problem evident right away. In extreme cases, memory corruption can cause the operating system itself to become unstable, leading to system lockups. Perhaps the worst outcome is when the program doesn't crash immediately, but exhibits strange, hard-to-diagnose behavior. Such bugs are difficult to trace and can waste a lot of development time. To prevent such bad outcomes, always stay within the defined array size. Off by 1 error happens when the array subscript you're using is just 1 unit away from a correct value, usually because you start counting from 1 instead of 0. So in this code, the loop starts at 1 and it goes up to number's size, which is a number's 100, because it set a condition like count less than or equal to size. The number's subscript size doesn't exist, leading to undefined behavior. Off by 1 error are particularly nasty because they may not cause immediate obvious issues. Your program may seem to work fine in some cases, but fail in others. So remember, in the arrays, the last element subscript is always n-1, where n is the size of the array. C++11 introduced a very convenient feature for array processing called range-based for loop. The traditional for loop requires a counter variable, and there's a risk of stepping outside the bounds of the array, leading to undefined behavior. The range-based for loop uses simple, clean syntax. It automatically knows the number of elements in the array, eliminating the need for a counter variable. One of the significant benefits of using this loop is that it handles bounds checking automatically, eliminating the risk associated with a manual indexing. Let's take a look at this for loop. Data type. This is the data type of range variable. For example, if you are iterating through an array of integers, then data type will be int. Range variable is the variable that will hold a copy of each element in the array as the loop iterates. It can be named anything you like, and it's locally scoped to the loop. Array is simply the name of the array you are iterating over. It could be a static array, std, array, or even a container like the vector. Statement. This is the code that gets executed in each iteration of the loop. This is where you put the logic that you want to apply to each element of the array. If you have more than one statement that you want to execute within the loop, you can enclose them with a braces to form a block of code. The array numbers is initialized with 5 integers. This array is what we will be iterating over. The line 4 integer val numbers, you can also use auto, AUTO, val numbers, is where this magic happens. Here, if you use auto, it infers the type of elements in the array, so you don't have to specify it. In the slide, it is specified as int, but you can also use auto, 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 so the compiler will look at the array and specify for you. The val is our range variable. It will receive a copy of each element from numbers array during each iteration. Inside the loop, we simply print the value of val. This will happen once for each element in the numbers array. So when the code runs, it will print each value in the array, each on a new line. By default, the range variable in a range-based for loop contains a copy of the current array element. This means you cannot use it to change original array elements. If you want to modify the array elements during the loop, declare the range variable as a reference by adding an ampersand before its name. Using a reference allows us to modify the original array elements directly without affecting a copy. This is important for operations like sorting, updating, or transforming an array. This example showcases how you can use the range-based for loop for both input and output operations on an array. We have defined an array numbers with a size, which is set to 5. We use integer %val to take input from the user and directly store it in the original array. The ampersand makes val a reference to the actual array elements. A reference is important here because we intend to modify the array elements with the values that the users inputs. The second for loops iterates through the array and prints each value. We don't need a reference here because we are not modifying the array, just reading it. The program then displays the array values one at a time. This is a simple read operations, so no reference is needed. As we mentioned earlier, the auto keyword allows the compiler to automatically infer the type of a variable at compile time. This can be particularly helpful when working with complex data types or when you want to make the code more maintainable. So use auto, then $val. Instead of specifying the data type explicitly, the compiler will automatically determine the type based on the array. The keyword auto infers the type of elements in the array. This is particularly useful when the data type of the array may change, as you won't have to update the loop variable's type manually. Using auto makes the code less verbose and therefore easier to read and understand. Range-based for loop is ideal when you simply want to step through the elements of an array without needing to know or manipulate the element subscripts. It is cleaner, less verbose, and minimizes the chance of off-by-one errors. The traditional for loop is used when you require the element subscript for some operation, such as accessing a parallel array or for advanced indexing calculations. It offers more control but comes at the cost of verbosity and the potential for errors, especially off-by-one errors. So if you're using just displaying the elements of an array, the range-based for loop is simpler and more intuitive. However, if you're trying to swap elements or use the index for some other operation, then the traditional for loop will be more appropriate. Array elements can be treated just like ordinary variables of the same type. That means you can perform various operations on them, including using increment, plus plus, and decrement, minus minus operators. Also, array elements are like regular variables. The context in which they are used can change the behavior of the operation like plus plus and minus minus. In the expression tests bracket I plus plus, the value stored as the test I will be incremented by 1. This is very straightforward and similar to using plus plus on a regular variable. However, test bracket or subscript I plus plus will simply increment the value of the index I, and it won't affect the element test bracket I. This can lead to potential confusion and errors, especially for those new to programming. So be very careful about where you place the plus plus or minus minus operator. Wrong placement can lead to bugs that are difficult to trace. When using plus plus or minus minus operators, ensure you are affecting either the array element or the index based on your intention. Misplacement can lead to unexpected behavior. Sometimes you might need to copy an array. The way you might think to do it by simply assigning one array to another doesn't actually work in C++. Arrays in C++ are essentially pointers to the first element of the array. When you try to assign one array to another, you are attempting to assign one pointer to another, which C++ doesn't allow for arrays. The correct way to copy an array in C++ is to do it element by element using a loop. This makes sure that each value is individually copied from the source array to the destination array. You will loop through each index from 0 to array size minus 1 and assign each element from the source array test bracket I to the corresponding element in the destination array new test bracket I. This is straightforward and works well for small arrays, but be mindful that this approach can be inefficient for very large arrays. C++ allows some specific ways to interact with arrays of different types. When it comes to character arrays, the language offers a shorthand for outputting the contents. If you have a character array like F name holding Henry, you can directly display its contents by setting its name to cout, as shown on this slide. The cout object recognizes a character array as a no-terminated string, and it goes on to display each character until it reaches the no character, which is a \0. This is automatically appended to the character arrays initialized with string literals. This is a special behavior for character arrays. It doesn't work for arrays of other types like integer or floating point numbers. Trying to output those directly will not give you the array contents, but may lead to unexpected behavior like displaying memory address. So character arrays are unique in how they interact with cout. You can directly display them, but remember this is a special case and it doesn't extend to other array types. So for the arrays of other types like integer, floats, and custom objects, we have to manually loop through each element to print it. The common approach for printing arrays of types other than characters is to use a loop. You go through each index of the array and print the element at that index. The code on this slide, we use a for loop and it starts with I equals 0 and it goes up to array size -1. Inside the loop, we use cout to print the value stored at each index I of the array named tests. Unlike character arrays, other types of array do not terminate with a no character, and C++ doesn't know how to interpret them as a single object to print. So you have to tell it explicitly which elements you want to print. The range-based for loop automatically iterates over each element in an array without the need for a counter variable or explicit length. In this code, we use the new loop style to print out each element of the numbers array. The val variable takes on the value of each element in the array one by one, and we print it inside the loop. So this feature simplifies your code and make it more readable. It also reduces the chance of off-by-one errors that can occur when you're using traditional for loops with the explicit counters. To calculate the sum of all elements in the array, we initialize a variable sum to 0. We then loop through each element of the array, adding its value to sum. The loop counter t_num ranges from 0 to size -1. Once we have the sum, calculating the average is straightforward. We divide the sum by the total number of elements, which is the size, to get the average. Note that we use double for sum and average to accommodate potential decimal values, even if the array elements are integers. This is especially important for calculating the average, which may not be an integer even if the elements are. So calculating the sum and the average of an array is easy using a simple loop for summing elements and a single line of code for averaging. Before entering the loop, we initialize an accumulated variable total to 0 and declare another variable average to store the result. The range-based for loop iterates over each element in the array scores. The variable val takes one value of each element one by one. Inside the loop, we add each val to total. This way, Total will contain the sum of all elements in the array once the loop is done. After the sum is calculated, we proceed to calculate the average by dividing total by num-scores, which represents the number of elements in the array scores. The range-based for loop makes the code cleaner, more concise, and easier to read, eliminating the need for explicit index manipulation. Sometimes you need to find the highest value stored in the array. We start by initializing the variable highest with the value of the first element of the array. This gives us a starting point for comparison. A for loop starts its iteration from the second element, count equals 1, to the last, count less than size. Inside the loop, we use an if statement to check whether the current array element numbers subscript count is greater than highest. If the current element is greater than what's stored in highest, then we update highest with the new maximum value. When the loop finishes, highest will contain the maximum value present in the numbers array. So the algorithm efficiency finds the highest value with a single pass through the array, making it a big O AND operation. Similar to finding the highest value in an array, you may also need to find the lowest value. So we initialize the lowest variable with the value of the first element of the array, providing a basis for comparison. A for loop starts iterating from the second element, count equal 1, through to the last element, which is count less than size, which is a size minus 1. Inside the loop, an if statement checks whether the current array element numbers subscript count is less than lowest. So if the current element is less than lowest, we update lowest with this new minimum value. So by the time of the loop concludes, lowest will contain the minimum value present in the numbers array. Sometimes you might not know in advance how many items you will need to store in an array. In such cases, a common approach is to declare an array that is large enough and use a counter variable to track the actual number of items. Make the array large enough to hold the largest expected numbers of elements. When comparing two arrays, you cannot use a single equality operator to compare all elements. You need to compare each element one by one. A flag variable, arrays equal, in our example, is used to keep track of whether the arrays are equal as we go through the loop. A loop counter, count in our example, is used to loop through each element in the array. A while loop is used to compare each pair of elements until the arrays are found to be not equal or until every element has been compared. If any pair of elements are not equal, the flag variable is set to false and the loop exits early. This makes the comparison more efficient. After the loop, we check the flag variable. If it's true, then all pairs of elements were equal, and hence the arrays are equal. Parallel arrays are a simple but effective way to manage related data when you don't have access to more complex data structures like classes or structs. The key to parallel arrays is that related information is stored at the same index in each array. For example, if we know that Bob is at index 1, In the names array, we can find Bob's grade at index 1 in the grades array. The arrays in a set of parallel arrays can be of different data types. For instance, we can be of type string to store names, while another can be of type integer to store grades. They are often used in programs that must manage small sets of related data, like student gradebook, inventories, or basic record-keeping tasks. This is not the most efficient way to store related data. Languages like C++ have structs and classes that can bundle different data types together, making the code easier to maintain and understand. In this example, we have 3 parallel arrays, ID, average, and grade, each of size 5. The ID array holds the student IDs. The average array holds their course averages, and the grade array holds their course grades. We use a for loop to go through each element of these arrays and print them out together. This is possible because they are parallel arrays. The ith element in each array corresponds to the same student. In a real-world application, you'd likely get these values from user input or a file, which isn't shown here for simplicity. Managing parallel arrays can get complex, especially if you have to sort, insert, or delete elements. You have to perform the same operations on all arrays to keep the data aligned. This program used 2 parallel arrays to manage employee data, especially their working hours and pay rates. So this is a program, and first we include IOStream and IOManip header files for standard input-output and formatting. We declare a constant integer num_employees set to 5 to determine the size of our arrays. 2 arrays are then declared: hours to store the hours worked by each of the 5 employees, and the pay rate to store their respective hourly rates. The program prompts the user to enter data for each employee. A for loop is used to iterate through each employee index. For each iteration, we ask for and store the hours worked and the pay rate for each employee. Using parallel arrays allows us to keep related data synchronized. Each index in one array corresponds to the same index in the other array, making it easier to manage related data. The main objective for this part of the program is to calculate the gross pay for each employee and display it. We start by setting the output stream to display floating point numbers in fixed point notation with 2 decimal places. This ensures that the output is easy to read and consistent. A for loop iterates over each employee's index. Inside the loop, we calculate gross pay for each employee by multiplying the hours worked, hours subscript index, with their pay rate, which is a pay rate subscript index. The gross pay is then displayed alongside the employee number. We ensure that the dollar amount is displayed with 2 decimal points for clarity. This is where the concept of parallel arrays truly shines. We have kept related data synchronized between 2 arrays, making it straightforward to perform calculations like this. The hours and the pay rate arrays are related in that they share common subscripts. For example, hours subscript 0 in the pay rate subscript 0 pertain to the first employee, hours subscript 1 and the pay rate subscript 1 pertain to the second employee, and so on. It is crucial to maintain the alignment between the two arrays. For example, if we modify one array, we should be mindful of the other array to ensure the data remains consistent. Think of a subscript as a key that unlocks corresponding data in each array. For employee I, hours subscript I provides the hours worked, and the pay rate subscript I provides the pay rate. Together, they can be useful to calculate the employee's gross pay. In our example, we had a for loop that iterated through the arrays using an index variable. This index variable served as the common subscript to access related data in both arrays. To pass an array to a function, you only need to specify the array's name without the square brackets and the size. For example, show scores. Then inside parentheses, we just pass the name of the array, which is a test. When defining a function that takes an array as an argument, you use square brackets but leave them empty in both the function prototype and header. For example, function prototype, void show scores, then integer, empty bracket. Function header is a void show scores, integer tests, and an empty bracket. The empty bracket indicates that the function expects an array. The function doesn't need to know the size of the array, but it will usually be guided by another parameter or a sentinel value within the array. Note that in C++, when you pass an array to a function, you are actually passing a pointer to the first element of the array. This is efficient as it avoids copying the whole array. The type of the array and the type in the function declaration must match. If your array is of type double, your function parameter should also be of type double, empty square bracket. Make sure to pass arrays of the correct type and be cautious when modifying the array inside the function, as it will reflect in the original array. When you pass an array to a function, the function doesn't know the size of the array. This can be a problem if you want to iterate through it. You can pass both the array and its size to the function, like show scores, and we have test in the array size. For the function prototype and the header, you need to add an additional parameter. So function prototype, we have a void, show scores, and the integer, empty bracket. The second parameter is a int, integer type. And for the function header, we say void, show scores, integer, and we specify the array name, test, empty bracket, then integer size. Inside the function, you can use the size parameter in loops to iterate through the array elements. This simple program shows how to pass arrays to functions while also providing the array size. When the function receives an array, it's essential to know the array size for iteration and manipulation. This function prototype is declared as void show values, and we have two arguments. The first one is the integer array, and the second argument is the size of the array. The main function initializes an integer array called numbers and a constant array underscore size that holds the size of the array. It then calls show values by passing numbers in the array underscore size as arguments. The showValues function takes an integer array, nums, and an integer size as parameters. Inside showValues, a for loop iterates over the array using the provided size and prints each element. By passing the array size, the function can accurately iterate through the array, avoiding out-of-bounds errors. When the program runs, it will display the array elements separated by a space. When you pass an array to a function, you are essentially passing a reference to the array, not a copy. This means any changes made to the array inside the function will affect the original array in the calling function. Understanding it is crucial because it impacts how the data in a program can be altered. If you are not cautious, you could inadvertently modify array data when you didn't intend to. You can imagine a two-dimensional array like a table in a spreadsheet. This table has both rows and columns, and each cell at a specific row and column holds a value. In this example, we have a constant integer rows equal 4, cols, which is columns, equal 3. So we can define a two-dimensional array using two size declarators. Integer exams, then the first inside the bracket is rows, second is cols. Recall our early example where we declare a two-dimensional array exams with 4 rows and 3 columns. To access an individual element in the array, you will need to use two subscripts, one for the row and one for the column. For example, to access the element in the third row and the third column, you would use exams, bracket 2, bracket 2. So exam bracket 2 equal 86. So this set the element in the third row and the third column to 86. Remember that the array index starts from 0, so the first row is an exam subscript 0, then subscript column. The first column is an exam, the subscript rows, and the subscript 0, and so on. So imagine the array as a 4 times 3 grid. The element at exams subscript 2 and subscript 2 will be found in the third row and the third column. This program uses a two-dimensional array to store and manipulate sales data for a company's different divisions and quarters. First, we define constants for the number of divisions, num underscore divs, and the number quarters, num underscore qtrs. When we declare a 3 times 4 array called sales, it will hold the sales data. We also declare total sales to keep track of the cumulative sales across all divisions and quarters. And the loop counter div and qtr will be used to iterate over the rows, which is divisions, and the columns, which represent quarters. We inform the user what the program does and asks them to input the necessary data. We have two nested loops iterating over each div, which is a division, and the qtr, which is quarter. Inside the inner loop, we prompt the user for the sales data and stored it in sales subscript div subscript qtr element. So this will ask the user to input the sales for each division and each quarter. We use another set of nested loops to go through each element of cells array and add it to total cells. Finally, we display the total cells figures in a formatted way. Here we use set precision and show point methods to ensure the output is displayed as a floating point number with 2 decimal places. So two-dimensional array combined with nested loops provide a powerful way to manage input and calculate multidimensional data. Here is the program's output. The program will prompt the user to enter the sales data for each division, each quarter. And then it will calculate the total sales and output the total sales. Initialization of a two-dimensional arrays is done row by row. Here, the first row is 8478, and the second row is 92 and 97. The inner curly parentheses can be omitted when initialization, and the C++ will still know how to separate the rows. If you don't provide an initial value for some elements in a row, those elements will be initialized to 0 for numerical types and the null for pointer types. You can initialize only the first few elements and leave the rest. Those will default to 0 or null for pointers. To pass a two-dimensional array to a function, the name of the array can be used as an argument when calling the function, similar to one-dimensional array. Here we have an example function call. It's a get exams. Then you pass the exams, which is the array name, then 2. The function prototype and the header should reflect the fact that the two-dimensional array is expected. Here the example is we first declare a constant integer cost equal to. Then we have a void get exams. Then inside we have an integer empty bracket. Then bracket cost, then comma, then integer. So this is the function prototype, and we don't need to really specify the argument's name. In the header, we need to specify the argument name. So the first is two-dimensional array. The name is exams. The second integer argument is rows. The empty bracket indicate that the function can accept any number of rows. The size declarator for the columns, which is COLS in this case, needs to be explicitly mentioned in the prototype and the function header. Inside the function, you can then iterate through each row and each column of the array as you would do in the main function. The function showArray takes a two-dimensional integer array as its first argument and the number of rows in the array as the second argument. You can also put a constant in front the integer array, empty bracket, then you have a bracket contains codes. So this constant quantified before the array argument ensures that the function will not modify the array. Here we didn't have const keyword. And the nested for loops are used to traverse each element in the array, row by row and column by column. The set W4 sets the width of the field to 4 spaces, aligning the output neatly. So here we have a separate function to display the array, makes the code more modular and easier to read. If you declare COLS, the columns as a constant, Constant helps to make the code more flexible and easier to update. Changes can be made to the array size in one place without having to update multiple parts of the code. We will discuss how to use the same function, showArray, to display different two-dimensional arrays and share the same number of columns. We define two 2D arrays in Table 1 and Table 2 with different row counts. So TBL1 underscore rows and TBL2 underscore rows respectively, but the same number of columns, COLS. So for Table 1, we will call showArray Table 1, comma, Table 1 underscore rows. And for the second one is for Table 2, we call showArray Table 2, comma, Table 2 underscore rows. The function can be applied to different arrays by changing the row count passed as the second argument. We prefix the call to showArray with an explanation of what is being displayed. For example, the contents of Table 1 are new line, and the constant TBL1 underscore rows, TBL2 underscore rows, and the COLS make it easy to change the dimensions of the arrays, and the function will still work correctly. We're going to look at how to sum all the elements in a two-dimensional array. For demonstration, we have a 5x5 array called numbers. We use constants num underscore rows and num underscore cols for the number of rows and columns respectively. Then we initialize this two-dimensional array by specifying values for each array element. The outer loop iterates through each row in the 2D array. The nested within the outer loop is the inner loop goes through each column in the current row. Inside the nested loop, we access the current element with numbers, subscript row, subscript col, and adding its value to our accumulated variable total. After both loops have completed, total will contain the sum of all elements in the 2D array. Then finally, we display the calculated sum using cout. In this example, we focus on summing the scores for each student separately to calculate their average. We have 3 students. Num underscore students is 3. And num underscore scores is 5. So we have 3 students and 5 scores for each one. The 2D array holds the scores. We initialize it. Each row represents 1 student and each column contains their scores. We use total to accumulate the sum of scores for each student and the average to hold the average score. The outer loop iterates through each student, which is row, in our 2D array. We reset accumulated total equal to 0 for each new student. So inside the inner loop, it sums up all the scores for a specific student. So here we have a for loop from colon equals 0 to colon less than the number of scores. After the inner loop completes, the accumulated total contains the sum of all scores for 1 student. We then calculate the average. Each student's average score is displayed in the console. We use row plus 1 to display the student number starting from 1 instead of 0. In this segment, we will look at a slightly different scenario, computing the average score for each test, which is the column in our 2D array, rather than for each student. The variable initialization are the same. So this code calculates and displays the class average for each test using a two-dimensional array. The outer loop iterates over each test represented by columns in our 2D array. The variable COL keeps track of which test, which is a column, we are currently processing. And the total we set to 0. In the inner loop, the nested loop goes through each student score for the current test and adds it to the total. So the inner loop is for integer row equals 0, row less than num underscore students. Then after the inner loop completes, we find the class average for the current test by dividing the total score by the number of students. Then the program displays the calculated class average for each test. And here we use the col plus 1 to convert the zero-based index to a more human-friendly format. While two-dimensional arrays are widely used, sometimes we need more dimensions to represent more complex data structures. Rect solid is a 3D array with the dimensions 2 times 3 times 5. Time grid is a 4D array with dimensions 3 times 4 times 3 times 4. Multi-dimensional arrays can be used for modeling physical spaces, simulating time series data, or representing higher dimensional mathematical constructs. To access an element, specify its coordinates in each dimension. We have a rect solid subscript 1, subscript 2, subscript 4. So when you pass a multi-dimensional array to a function, all dimensions except the first one must be specified in the function prototype and heading. Why omit the first dimension? This is because arrays decay into pointers when passed to a function, but the function still needs to know the sizes of other dimensions to correctly manage the data. Vectors are part of a standard template library, STL, and offer a dynamic, resizable array-like structure. Unlike arrays, they can grow and shrink at runtime. Vectors can hold values of any data type. Just specify the type within the angle brackets. One of the significant advantages of vectors is that they automatically resize. You don't need to specify the size at definition. You can add elements to the end of the vector using push_back function. Pound sign include vector, so always remember to include the vector header file when using vectors. Vector, angle bracket integer, then scores. Here we declare a vector that will hold integer elements. It starts with 0 elements. Vector, angle bracket integer, then scores. And in the round parentheses we specify 30. So here we declare a vector of integers within an initial size of 30. The elements are uninitialized. They may contain garbage values. So we have a vector, angle bracket integer, then scores. We have a 2 argument 30 and a 0. So it declares a vector with an initial size of 30 and initialize all elements to 0. Vector angle bracket integer, then finals scores. This declares a new vector finals and initializes it to have the same size and the contents as the existing scores vector. So here in the round parentheses, we pass the scores, which is the vector we declared before. In C++ 11 and later, you can initialize a vector with a list of value enclosed in curly braces. The push_back function allows you to add elements to the end of the vector. This is especially useful when you don't know the size of the vector in advance or when the vector is full and needs to be expanded. Vectors in C++ are dynamic arrays, so they can grow or shrink at runtime. The push_back function takes care of the resizing for you. The size member function returns the current number of elements in the vector. The pop_back function removes the last element from the vector, effectively reducing the vector size by 1. The clear function removes all elements from the vector, making it empty. The empty function returns a boolean indicating whether the vector is empty or not. This is useful for loop control or conditional statements. In this program, we define and initialize a vector named numbers with integers. We then use a range-based for loop to iterate over each element in the numbers vector. For integer val, then colon, numbers. So here, the type of elements in the collection is an integer. Val, V-A-L, is a variable that will hold the current value in this collection. And the collection we're iterating now is a vector. So the advantage use range-based for loop is it simplifies the loop, makes the code easier to understand and maintain, and eliminates the chance of off-by-one errors. The program will display each element in the numbers vector. The vector class provides several useful member functions to manipulate and query the state of vectors. So at round parenthesis I, it returns the value of the element at position I in the vector. Capacity, it returns the maximum number of elements a vector can store without allocating more memory. Reverse member function, it reverses the order of the elements in a vector. Resize and val, it resizes the vector so it contains n elements. If new elements are added, they are initialized to val. Swap, vect2, so exchange the contents of two vectors. Note at I function will throw an exception if the index I is out of bounds, so it will give you error if I is out of bounds. The capacity function can be useful for optimizing performance in some cases.